Hello and welcome to yet another video on this channel. In this problem, we need to prove that given a group G and the two subgroups of G as H and K, we have to prove that the intersection of these subgroups H and K is indeed a subgroup of G. Now let's visualize the set structure over here. So let's imagine that this particular box over here is the group G, and let's imagine that this circle is the set H. I mean, we're just looking at the set structure as of now because it is easier. And this particular circle here is the set K corresponding to the group K. And we need to show that the intersection of H and K, the common region, is a subgroup. So what are the properties of a subgroup? So the properties of subgroup, the first property is that it should be non-empty, correct? The second property of the subgroup is that the set structure of the subgroup should be a subset of the set structure of the group G. And thirdly, we need to show that if A and B belong to the subgroup, then if A and B belong to the subgroup, that would imply that A multiplied by B inverse also belongs to the subgroup. So these are the three properties that we are going to prove over here. Okay, let's get down to work. First of all, we know that 1 is the identity element, right? 1 is identity element. Let's assume that 1 is the identity element, in fact. So let 1 be the identity element of of G. So if 1 is the identity element of G, then 1 belongs to both the subgroups, right? 1 belongs to H and 1 belongs to K. And since 1 belongs to H and 1 belongs to K, we can safely say that 1 belongs to H intersection K. And that actually shows us that our particular H intersection K is non-empty, right? That shows that H intersection K is non-empty. Okay, now let's assume that A, B belong to, okay, so before that, subset, right? So, um, so H elements, the elements of H, right? The elements of H intersection K, elements of H intersection K are also elements, are also elements elements of H, right? I mean, equivalently, you can say that these are also the elements of K, but they mean the same thing. So since all the elements of H intersection K are elements of H, so the elements of H intersection K, the elements of H intersection K are also elements of G, right? And this shows that H, the set structure of H intersection K, is a subset of the set structure of G. So the condition 1, the first condition of non-emptiness is satisfied here. The second condition of subset is satisfied here. Now let's look into the third property. Okay. In the third property, let's assume that A and B belong to H intersection K. So what is the aim over here? The aim over here is to show that A, B inverse is a subset, is an element of H intersection K. Is this true or is this false? Okay. Now since A and B both belong to H intersection K, what happens is that A comma B belong to H and A comma B belongs to K as well. Now since H and K, so since H and K are subgroups, right? Are subgroups. So both of them satisfy that A and B, both of them satisfy, pardon me, A, B inverse belong to H and AB inverse belongs to K, right? And since AB inverse belongs to both H and K, therefore we can say that AB inverse belongs to H intersection K. So all our three properties are proved now, and therefore we can say that H intersection K is a subgroup subgroup of G. And that, my friends, finish the proof over here. Thanks for watching.